So today we're going to be finding the maximum angular velocity that we can spin a cup with liquid in it before that liquid will spill over the edge. So for starters, our cylindrical cup has a radius of r and a height of h. And to simplify things, we're going to say that our initial liquid height is also equal to the radius of the cup, or big R. And then our cup is also perfectly cylindrical. Okay? And then, so we're going to be solving for omega in this case, which is equal to angular velocity. And in our system here, where we have a cup with radius r and height of h, our liquid level is going to start off as the same value as our radius, and we eventually, as we spin it faster and faster, we will end up with something that looks like this. This point may be a little lower, depending on our system, where again we have h, and basically this is what we're solving for. We're solving for the omega, the angular velocity at this point. And so what we'll need to do that is basically at any radial point from the center. So at any radial point, which we're going to use a small r, just do r prime there, or r1, corresponds to a given height of that liquid at that point. So we'll do an h and an h1. And basically by doing this, we are going to be able to simplify and find an equation that corresponds to the maximum angular velocity. So actually I made a mistake. Our small h value is actually from the bottom point of this parabola to the height of the liquid, not from the bottom of the container. And I'll talk about why in just a minute. And so we can actually get an equation for this small h, the height of the liquid relative to the bottom of the dip. And to do that, we're going to start out with our basic equation of statics, which is dp over dr, and that is equal to the density, rho, omega squared, our angular velocity squared, r. And then from there, we're actually just going to integrate both sides, and we're going to put our dr over here so it's easier to integrate. So we have our change in pressure on this side, and then our constants, density and angular velocity, we'll keep that outside, and we'll integrate the r dr. And from that, we get P is equal to density, angular velocity squared, radius squared, and this again is our small r radius from any point along this line. Again, big R is the full, and that is over 2. And so what we can do with this to get our h is substitute in for P. We get rho gh, our density, our gravity constant, and then the height. So if we get rho gh equals density, angular velocity, r squared over 2. Our densities cancel out, then we move g down here, and we get our h is equal to omega squared r squared over 2g. So if we use the knowledge that the volume doesn't change between our starting system and our cup at maximum angular velocity, we can use that to separate this out and find that the bottom portions and these top portions are both equal in volume and in amount of liquid. The bottom portions obviously are the same, but then this top section, the volume is the exact same as this. But using this height of this top section, we're able to formulate an equation that we'll need later for the total height of our cup, which is equal to R, which is the starting height of our liquid, and then minus this top section, and then plus our small h, the height at any radial point, but only when small r is equal to the full radius, basically when the water is at the very top of the cup. And then with our volume, we're able to solve for volume. So since the volumes are equal, it is way easier to do it to find the volume of the top section on this side, which is simply just pi r squared h, or in this case we're going to do d. And then if we look at what's changing in relation to the change in our radial point, so dr, we can find that dv, since volume changes as well, if you look up here, if r changes, volume will also be changing. So we get dv, and then that is equal to h. We'll replace d with h in this case, since now we're looking at this diagram. So h pi r squared, and then dr. And sorry, since we are basically differentiating this first equation, it's going to be 2 pi r and then dr. And now what we're going to do is we're going to take an integral of this, and we're going to replace h with our angular velocity. So we have the integral of dv, which is just v, but we'll keep it there. And then 2 pi, and then our h, which is our omega squared over 2g. And then we're gonna, well, it's omega squared r squared, but we're gonna combine our r values. It's gonna be r cubed dr. And since these are constants, our radial point is changing. That's what we're looking at. We can just put that under the integral. And after simplifying this here, canceling out the 2 and integrating, we get our velocity is equal to pi omega squared over g. And then we have r to the 4 over 4. And then we're going to be using this to solve for our omega, or our angular velocity. So using this equation to solve for d, just by simplifying, we can get that d is equal to our omega squared times our radius squared over 4g. And remember that our h that we solved for previously is also w squared r squared over 2g. And so now we're going to take the equation that we got from our diagrams earlier. So our h is equal to big R minus d plus plus H when R is equal to big R. And that's that equation right there. So now by plugging in, we get H is equal to R minus our omega squared, R squared over 4G, plus our omega squared, R squared over 2G. And then we're gonna get H and R on the same side and combine like terms over here. So we have H minus R is equal to W squared, R squared over 4G. And now we can solve directly for the angular velocity when R is equal to the full radius. And that is going to look like our omega is equal to 2 times the square root of G H minus R, and that is over big R. And so this equation is the maximum angular velocity and the speed at which we can spin our cup to where the liquid will rise up to the lip of the cup, but it will not spill over. Thank you.